Alrighty, Chapter 17, the Earth's interior and geophysical properties and geophysics in general. The reason I kind of start with this image, I'll talk about it a little bit later on, is this was kind of neat. I mean, I grew up and I kind of watched Jurassic Park when I was, I don't know, 10 years old or something. And the technology they used for this shot is something that sort of didn't hardly exist then, or it wasn't widely used, and now we use it quite widely, and it's called GPR, and I'll talk a little bit about it later on. But it's just kind of neat where this is, kind of like Star Trek, right? There's those things they had in Star Trek, like tricorders and tablets and things that now exist today, and it's sort of, sci-fi influenced modern society, and it may have happened a little bit here too. Also, I really just want to take this opportunity to hit home and make the statement that the first Jurassic Park is the only good Jurassic Park, and you'll be expected to put that on a test too. So, very important. So, the Earth's interior. How do we study it? Well, we study it indirectly. We can't drill down into the Earth, not very deep anyway. The deepest we've ever gotten is about 12 kilometers, which, is what, like 7 miles. We just can't drill very deep. The pressures that exist deep in the Earth, even past a few miles, are insanely great. And the engineering hurdles that exist to try and drill down that far are just too much. We don't have the technology to do that, and I seriously doubt we'll ever have the technology to really drill through the Earth past much more than a few miles. So since we can't do that, we study the Earth indirectly, and the tools we use we kind of call geophysics, because a lot of it deals with the physics of the Earth and just the mathematics of how we study what we can about what we can see about the interior of the Earth. And the main tool we use, the main feature we use, are seismic waves. And I mentioned this in the earthquake chapter about how we can sort of listen to the seismic waves and study them to determine what the inside of the Earth looks like and what it's made out of. And the two big things are seismic reflection and seismic refraction. And like I mentioned before, it's kind of, an earthquake sort of acts like a sonar ping, if you've watched any submarine movies. And we can listen with our seismic stations to what happens to those waves as they reflect off of boundaries inside the Earth, or as they refract off of these boundaries. And the way the waves act and the properties they sort of carry with them can tell us about what this boundary is and what's going on in this layer versus this layer. And these can be major layers. This could be the mantle down here, and this could be the crust up here, or it could be as simple as this is a sandstone and this is a shale, and you can tell the difference between this stuff based on these seismic waves. And with the refraction, it deals with how these waves move through these layers. So some layers, the velocities can increase, and in some layers they can decrease. And basically, the denser your layer, the faster your seismic waves can move through it. So, based off this information that we get from these seismic waves, we've been able to determine the boundaries of the crust and the mantle and the core and the different boundaries we have within those. So take a quick look at these boundaries. So here we have the crust that's super thin at the top, about a couple miles to maybe 50 miles thick on the thicker parts of the continental crust. It's very thin compared to the rest of the Earth, which is, I think has what, an 8,000 mile diameter or so all the way across. Miles. You can look that up. It's about that wide. So the way these seismic waves travel through the planet is why we think these layers exist, from the crust to the upper mantle, the outer liquid core, and the inner solid core, and we'll talk more about that here in a second. So with crust, we have oceanic crust, and the seismic waves that travel through it go a little bit faster than the seismic waves that go through continental crust. Why? Because oceanic crust is mafic. It's made out of heavier minerals and rocks. They're denser, there's more metals in there, and so seismic waves will travel faster through those denser materials versus the continental crust, which again is mostly made up of granite and other felsic rocks. Now the mantle, which again is, there's some magma in the mantle. There are some pockets of magma inside the mantle, but the majority of the mantle, it is a solid. It is solid rock. It's not all liquid like some people, I guess, think. And due to or the speed at which we see seismic waves travel through this, we think that the mantle is made out of ultramafic rocks, which are basically rocks that have even more metals in them and more darker minerals in them than even basalt. And some of these things are, let's see, peridotite, and stuff that has a lot of olivine in it, which is an iron silicate. But basically even heavier rocks than the stuff we looked at in the classroom. I mentioned ultramafic rocks a little bit when we classify igneous rocks. It's basically another row that you can add on to that classification scheme, and some rocks that you can sort of add to that. But anyway, beneath the lithosphere, so if you remember the mantle, we have, so we'll take a look at the cross section of the Earth here. I'm about to draw it. Normally we have the crust and the mantle. Well, we can also differentiate that into the lithosphere and the asthenosphere. And the lithosphere is basically the crust and the upper part of the mantle. We call the lithosphere, and everything beneath that we call the asthenosphere. So beneath the lithosphere, seismic wave speed decrease in an area where the mantle gets a little more plasticky. It's not super solid, and so we have this low velocity zone where the seismic waves slow down, and we call that the asthenosphere. And you can kind of see it in this little blip right here. And we'll look at that blown up later. So, with continental crust, we've got slower seismic velocities. With oceanic crust, they're a little bit faster, and with the mantle, they're even faster, except for the asthenosphere. And then we can figure out the densities of these rocks, one, just by measuring the densities of the rocks that we find, but also we can sort of backtrack it. When we look at the velocity of these seismic waves, we know that, oh, the density of these rocks are about this much in these areas, and they correspond to, felsic, mafic, and ultramafic. So here's a cross-section of the Earth, a little bit of ocean, a little bit of oceanic crust, nice big thick piece of continental crust. And so we have the lithosphere over here, which is the top part of the crust, and the crust and the top part of the mantle, and then the asthenosphere, which is beneath that, where you have a lower velocity area. But through this part, the upper part of the mantle, we get really higher velocities of seismic waves through the really ultramafic rock that's really solid here, and then beneath this it gets a little plasticky. And there's this thing called the Mohorovicic discontinuity, sometimes called MOHO. I won't go too much into that, but it is something that we see in the seismic waves, and it's how we differentiate the crust from the mantle. So here you go. Here we have the cross-section of the Earth, and we've kind of graphed it out, and we're looking at what the different waves and how their velocities change as they move through the planet. So up here we can see this low velocity zone in the asthenosphere, and then the higher velocity just underneath the crust. But we see as we go down through the mantle that our P waves, they increase in velocity as you get more and more pressure and more dense material from all that pressure. And then we hit the liquid outer core. We think the outer core is liquid because, one, S waves don't go through it. And we know S waves can't travel through a liquid. We can, sort of perform experiments here on the surface of the planet kind of showing that. And if you go back and look at S waves, I explain what they are and how you can't, shake a liquid basically. However, you can push a liquid. But when you get in this liquid area, the velocities slow way down until we get into the inner core, which we think is solid based on what the P waves do and also some astronomical modeling and some simple modeling of the materials that we think are down here. And S waves would move through this if they could, but we can't measure those because they just don't get out of the inner core. So, along with the seismic waves that pass through the core, we get these seismic shadows. And there's even a shadow for the P waves as well as the F waves. And so we can look at that, and that's due to the refraction of these waves. So we have an earthquake occurring up here. These waves travel through the planet. They get refracted as they cross a lot of things, but they especially get refracted as they cross the core boundary, and then again as they come through the other side, and it creates this shadow zone where we just don't, seismometers in these areas just don't see the P waves coming through, or even the S waves. However, they show up down here again. So with S waves, it's a really big shadow due to the fact that these waves can't travel through the liquids, can't travel through the outer core, which we think is a liquid. So the composition of the core is iron and nickel and other heavy metals that are down there, but primarily iron and nickel. And the density is quite dense at 10 to 13 grams per cubic centimeter. And it's calculated based on both, like I said, astronomical data, basically how we interact with the moon and the sun, and also what the seismic waves are actually doing as they pass through the material. There is the core mantle boundary, which is marked by what we call the D double prime layer. You don't have to remember that, but we see a massive, massive change in velocity at this boundary. So here we are again, looking at that. So, tools we can use. So, I mean, seismic waves, they don't just allow us to study the deep parts of the planet. They can also help us study the upper parts of the planet, and I'll go more in depth into this in the next chapter, in chapter 18. But we can do seismic surveying, where we basically create our own little thuds, and we listen to the reflections off of rocks and other material of this seismic information, these seismic waves, and it's how we can determine the location of oil and gas and other materials. And I'll kind of show you some of that actual data real quick. So here's some seismic surveying data, and they've actually filled in some of these layers with colors. But if you start to look, you can see faults. I didn't do that. How'd that happen? You can see these faults. And in particular, I'm going to kind of just zoom in on this area. We can actually try to figure out what kind of faults these are. So here's a fault here. There's a fault there. And we see this layer right here, right? Well, it connects up with this layer up here and this layer over here. So that means this area has been pushed down. And this is the hang wall, and this is the footwall. And so when our hang wall has gone down compared to the footwall, that's a normal fault. And because of that, I know that the forces in this area for this fault were tensional, as being pulled apart. But primarily the reason we look at this stuff is as a geologist, as an exploration geologist, if I'm trying to find oil, oil can get trapped along these faults where you'll have a big sandstone, that comes up to the fault, and then if all of a sudden the sandstone doesn't continue and it runs into, a shale or something, then that can be in an aquitard, right? Something where things just don't flow through it, including oil. So the oil can kind of get trapped in this area in that sandstone. So me as an exploration geologist tries to find these areas, and I say, you know what, let's put an oil rig over here, risk a couple $1,000,000, and drill down here and see if we can find this oil. And I mean, this is essentially what happens. I've not quite looked at this before, up until a little bit ago. And so you'll actually get this kind of data as an exploration geologist, and you'll try to go through it. And there's software that can kind of help identify these things. But you'll try to find the geologic structures in here, in these formations, and where you might find oil and gas being trapped. And you try to convince other people of it, and go spend a bunch of money to try and go recover that resource. Other tools we can use, geophysical tools, are gravity meters to search for gravitational anomalies kind of under the ground. So something you may not know is there is gravity between everything. It's not just the planets orbiting each other. There is gravity between me and you right now. There's a slight gravitational pull. It is very, very small because the gravitational force is very insignificant, but it's still felt over great distances. But if I take a little gravity meter and pass it over an area where there's a dense metallic core, then it will, that meter, the little sensor that's in there, will actually be pulled, or the mechanism that's in there will be pulled towards this metallic ore, versus the opposite. If I pass over a cave or an area that's maybe got a bunch of water in it, it'll do the opposite. And so we can use gravity meters to kind of detect this stuff, which is kind of neat. And this is used fairly heavily with satellites. So ore bodies, like I just showed, can show positive gravity. Magnetite, more mafic minerals and rocks, and then negative gravity, so water, sediments, more felsic stuff, open areas like caves. So fairly useful. If you're trying to build something, a highway or something, you might take some of these gravity meters over an area. If you're worried about caves, you can try to detect those caves before you put your road in. The Earth also has a magnetic field. So there's magnetism that we can use to try and study the Earth. The Earth is basically like a giant magnet all on its own. And something that happens are magnetic reversals, where this giant magnet that the Earth is sort of flips back and forth what seems to be completely randomly. Now the whole planet doesn't like turn itself over. It's just that the magnetic field does it. In fact, our magnetic field, the North and the South Pole, the magnetic North and South Pole, not the thing we spin on, not the North and South Pole, the geographic North and South Pole, where the Earth's axis actually spins on, but the magnetic poles actually wander around quite a bit, and you have to, if you're ever using a compass in a very precise manner, you have to adjust for that. Like you can go to the very geographic North Pole, but the magnetic North Pole may be several hundred miles down south in Canada, and so your compass won't actually point to the North Pole. It'll point to that magnetic pole. Anyway, like I mentioned, this thing reverses, and we've used it to help out with geologic time and the whole geologic time scale. What happens is when we get, I'll just fast forward here, when we get igneous rocks that are coming up out of volcanic areas, especially mid-oceanic ridges, the little ferromagnetic minerals that are in that magma, the really small minerals, will align themselves like a compass with the Earth's magnetic field. And so when we have these ridges that are spitting out all this magma, we'll get these stripes. If you look at all the rocks along this area, you'll see that the ferromagnetic minerals in them sort of will point one way, and then in the next strip of land they'll point the other way. And so it kind of looks like this. And so we can use the oceanic crust to determine when these magnetic reversals occurred. But also when we looked at this, it helped us to understand how the oceanic crust was being generated anyway, and it was kind of the mechanism that gave us plate tectonics. So we've talked a little bit about that before. So here's kind of what that looks like. The hotter colors are the younger rocks at these mid-oceanic ridges, and then the cooler colors are the older rocks. So kind of neat. But in addition to that, we can use these reversals to help us correlate sedimentary rocks in the geologic time, or not just sedimentary rocks, but rocks in general. So over here on these columns here, so this is geologic time scale if I haven't shown it to you before. And it goes from here down, and then it connects back up here and goes down, connects back up here and goes down, and connects back up here until you're at the beginning of the Earth down here. And this isn't to scale. This is the Cenozoic, so this only goes back 65 million years. This is kind of the age of the dinosaurs. Mesozoic, so you're at 65 to 252-ish. And Paleozoic, which goes back, which is 252-ish to 540-ish, and then 540-ish, all the way back to 500, or sorry, all the way back to 4.5 billion years. But you can see over here, we've sort of created a time scale with the magnetic reversals. I'll zoom into that real quick. So here in present time, we kind of have a normal magnetic field where north is north and south is south. And then these wide areas, it's where it's reversed. And it seems to be completely random. We don't know when it's going to switch. And you even have periods back here, like during the Cretaceous, where it didn't switch for a long time. But yeah, it's kind of neat. Our igneous rocks act as basically compasses that get frozen in time whenever they solidify coming out of the volcano, or whenever they solidify underground. Anyway, that's called paleomagnetism. And it's this whole sort of branch of geology. Remember that. Maybe I'll ask you what that is on a test. So with the Earth's magnetic field, we also see magnetic anomalies, which are basically changes in the Earth's magnetic field, over different areas of geology. So just kind of like how you can do with the gravity meters, you can also use magnetometers to discover odd areas underneath the surface of the Earth. So something like magnetite, which is very magnetic. Remember, it attracts a magnet. We can see this positive magnetic anomaly when we run a sensor over it. Same thing for a very mafic dike, and so on. There's a lot of different ways that you can use this, similar to how we kind of use gravity meters. In addition to using it on just the Earth, we can also use it in space. And using magnetometers and gravity meters and other remote sensing tools, we can study the surface of other worlds like the moon. And we can actually determine a lot of features like these things right here, which you couldn't otherwise see very well just looking at the moon. And if I remember right, these are basically spreading centers, just like our mid-oceanic ridges that existed on the moon for some time. And you see that there aren't very many craters here, so I assume this chunk of the moon is probably a lot younger than these areas that have more craters. And I don't know a whole lot about the moon. I'm just making an observation about that, and I bet you I'm right. So yeah, at one point you would have had these large volcanic areas on the moon creating new crust. Other tools that we can use, I wanted to mention this, oil and gas geophysical tools. So these are things I used to use whenever I worked on oil rigs. And the thing you can say all sorts of negative things about the oil industry if you want, but the thing that's hard to argue against is their technology is really advanced and really cool. The tools I got to use when I worked in the oil and gas industry were just really fascinating, and just how useful they were, and what they did. So one is gamma ray, a gamma ray tool, which is basically, so all of this data is for the same hole that's been drilled. So here we're at 7,000 feet, 7,100 feet, etc., down some hole somewhere, and you can put these gamma ray tools and resistivity tools, also conductivity, which is basically the same thing. It's just the inverse of resistivity. And then neutron porosity, this is something I didn't use, but a gamma ray tool basically will measure the amount of gamma radiation coming off rocks, and different rocks will have different types of gamma ray radiation. So it's really useful for identifying sands, and if you find sand, then you go, oh, there might be hydrocarbons trapped in this sand. Let's go drill down there. Or you might actually, generally if you're on an oil rig, you're drilling already in an area where you probably know where the material is, right? Sometimes you drill what's called a wildcat well, which is you're looking for the new stuff and you're using best guesses to sort of find it. And sometimes you're drilling, you know, a mile away from another oil rig, and you know that there's oil in this sand layer. You're just going a mile down the road trying to get more of it. And so you're looking for a certain sand formation. And so when you start to see it in your gamma ray log, you go, and you call your boss and say, dude, it's time to start turning the drill bit so we can drill horizontally into this sand and we can drink that milkshake. Resistivity will change based on the types of fluids you see. So basically hydrocarbons are more resistive than salt water. Salt water is very conductive. So again, I could also say conductivity. So salt water, very conductive, hydrocarbons not as conductive, so it'll help you figure out where this stuff is. So with this graph right here, I can see that, oh, in this sand layer, there should be a lot of hydrocarbons right in there. And then beneath that, it looks like I've got a brine. And then over here with neutron porosity, it's basically a measurement of the amount of hydrogen, I believe, that exists in an area, and it can help you figure out what the actual porosity is of the material that's there. And so here we can see that it's showing that there's gas, as in like natural gas, and then oil, and then the brine. So I know that there's natural gas above this layer. And honestly, this is sort of this isn't exactly what your graphs will look like, what your information will look like, but it's pretty close. It really is this kind of simple. Just looking at this stuff, and it's live data when you're sitting there on site and you're reading this stuff, and it really is. You'll see this information coming through it on your computer screen, and people get excited about it. Or sometimes you see things you don't expect to see, and you go, oh man, where's the sandstone? Where's the sandstone? Where's the sandstone? Oh no, there must have been a fault between here and a mile down the road that messed up this sandstone, and it's much deeper than what we thought, or maybe you hit it much earlier. But anyway, these are all geophysical tools that we basically drop down the hole, and measure this stuff. And like I mentioned from the beginning, I wanted to talk about this, the GPR. So if you remember from Jurassic Park, if you watch the movie, especially if you were in the theaters, they basically had this shotgun shell that they kind of shot into the ground, and it was very loud, and everybody jumped out of their seats. And then they went over here to this little screen, and they said, ooh, look, there's a velociraptor underneath the ground. And GPR it's not quite, it doesn't look, the data you get does not look like this. You don't all of a sudden see a velociraptor. I have, however, used this to look for fossils. We tried it out along a creek bed, which we knew it probably wasn't going to work because water tends to mess with ground penetrating radar. But it's basically miniature seismic data, right? You're using radar and you're making a big old thud, and or you're not making a big old thud, and you're just kind of listening. And in general, you're using kind of passive radar to try and tell what these layers are doing. But this is kind of the data that you see. So you'll notice there's something here, there's something here. This, I don't know where this came from. This might be some sort of conduit, electrical conduit. Maybe this is a water a water pipe or something, or you'll use this stuff to figure out where underground storage tanks are and anything you're looking at under the ground. So when we were doing this stuff, we were actually looking for what we would hope we might see is a big anomaly, and that may have ended up being like a mammoth tusk, or sorry, a mastodon tusk, which we had found in the area recently. But the water underneath the creek bed sort of proved to be a barrier to really letting us look very deep to find anything. But anyway, so yeah, that scene in Jurassic Park, it's real. Doesn't look like this, but it does produce something that looks kind of like this, and you might go looking for bones based on what you see with this kind of information. Yeah. Something I wanted to throw into here, this probably belongs more into chapter 15, but I didn't, there's so much in chapter 15 that I wanted to just not make you suffer with more. There's something called isostasy, and I've mentioned it before when we talked about glaciers, and it's basically the rebound of the crust. And so the crust will go through what's called isostatic adjustment. If I've got a mountain and I remove the top, the crust will rebound a little bit because I've removed a lot of that mass. I've mentioned before, when glaciers melt, the crust will rebound a little bit because you removed all that mass off of the crust. In addition to that, you can also take away part of the bottom, and the mountain will sort of adjust itself. So I just wanted to mention that that's what isostasy is, and we sort of see it here a little bit in the Ozarks. We got a whole bunch of erosion here in the Ozarks, and so we see a little bit of a crustal rebound in the Ozarks due to this isostasy. Most likely, we should be experiencing this. The Ouachitas certainly are. There's some arguments to say that the Ozarks actually haven't experienced isostasy. This is from me arguing with my professor at U of A. Actually, I didn't argue with him. It was something he argued, and I think it was a big argument at the geology department. But again, that was almost 20 years ago now, so maybe now they know more about the Ozarks and whether they've experienced isostasy or not. But at the time when I was in college, it was an argument. But when you do a lot of erosion off the top of a mountain, you should expect a little bit of crustal uplift to sort of push back up. And the analogy I'll use is it's kind of like a boat. If you've got a boat and you've got a whole bunch of stuff on the boat sinks, right? You take the stuff out of the boat raises up. This is something I especially saw in Hawaii. Over time, the Hawaiian Islands erode very quickly, and some of that rebound that the islands experienced in Hawaii probably allowed for a little bit of melting underneath, and it created these smaller volcanoes that you see all around Hawaii, like Diamond Head and Punch Bowl and all that, if you're familiar with Hawaii. If any of you guys ever want to go to Hawaii, you guys can look me up on Facebook or something. You can ask me all sorts of questions. I know those islands like the back of my hand just because I got to crawl all over them when I lived there. So this is just a map showing the crustal rebound from the last ice age when all of the glaciers retreated. So they've got these contours on there. And it's just showing how you can use contours not only for topography, but you can use them for other things as well. And it's just showing the amount of crustal rebound that's occurred since the last ice age. So every line is 50 meters of rebound. So here, this area has rebounded 250 meters since the last ice age. So this used to be 250 meters deeper when there was a big old glacier on top of it. Anyway, that's all I've got for this. Let me know if you've got any questions, and there should be a quiz on Canvas for this.